sleep at night and waking up in the morning. That's something we're very familiar with. So this is going to sleep at night and you wake up in the morning. But of course, sleep and wake are particular things that happen during our day, and they're associated with many other things that are going on in the body. So for instance, when we are about to go to sleep at night, as it starts getting dark, the hormone melatonin secretion begins. And then after about midnight, you start going to your time of your deepest sleep. At this time, your body temperature, which has a daily rhythm, goes to its very lowest level. Then as the sun comes up, your melatonin secretion stops. Soon after this, you start producing the hormone cortisol. And within a couple of hours of this, you have your highest levels of alertness. Then you go around to noon, and just after the noon, you have your peak coordination and concentration. And then in the afternoon is a time when you have peak cardiovascular and muscle strength. And then you go around again, and your melatonin secretion begins again the next evening. Now, these are the obvious things that happen. And these are all very important because we live on a planet which turns around once per day. Now, it's not only daily rhythms. These daily rhythms can change, and it depends where you are. So this is a photograph from Svalbard in northern Norway, and this is midnight in late June. So this is midnight, and of course, it's absolutely light, and it remains light throughout the whole of the day. If you go back to the same place in mid-February, this is midday in February. So it's dark for 24 hours. And the reason I just want to show this is that actually these sort of things matter to the animals that live there. These reindeer, if they had babies at this time of year, they would all die. There's absolutely nothing for them to eat. So what's really important is that they have yearly cycles in their reproduction so that they only have babies in the spring when there's lots of food around. So you have yearly rhythms as well as the daily rhythms, which I mentioned before. 50% of the adult population will be very used to this particular rhythm, which is the monthly rhythm. So this is in humans, the monthly reproductive cycle with the periods coming on once a month, ovulation occurring once a month. And this is monthly in humans, but in the rodents, it happens every 5 days. We're probably a bit less aware of lunar cycles and tidal cycles, but in fact, there's quite a lot of animals that live on the seashore which depend on the tides, and they actually have cycles determined by the phase of the moon. And finally, what I'm going to talk about quite a lot in this talk is ultradian cycles. And these are cycles which happen more frequently than once a day. And I'll talk about these in a little more detail a bit later. So let's get back to the daily cycles. So we live on this planet goes round, and every 24 hours you have periods of light and you have periods of dark. And this is really important for the body because the body has to adjust. It has to get ready for the activity of the working day, and then it can rest during the nighttime. And in order to do this, what's really important is that you can predict when light and dark will be. And you have in the base of the brain a little area called the suprachiasmatic nucleus, which is actually a body clock. This body clock, and this is where a few begins, if you just take it out and put it in a dish, you'll see that every 12 hours it turns on and off. So it's on, 12 hours later it's off, 12 hours later it's on, 12 hours later it's off. So it has an intrinsic rhythm of its own. It can predict when day is coming, which is very important because then it tells all of your hormones, all of your metabolism to get ready for the next active day. And it's kept accurate to 24 hours by light coming in through the eyes. So basically the system I'm interested in particularly is the hypothalamus producing a peptide called CRH, which acts on the anterior pituitary gland. The anterior pituitary gland makes the hormone ACTH, which goes around the body. It acts on the adrenal cortex, and the adrenal cortex makes a hormone cortisol. It's cortisol in man or corticosterone in the rat. And this then feeds back both at the level of the anterior pituitary and at the level of the brain. So you have the hypothalamus making CRH, acts on the pituitary, it makes ACTH, and that acts on the adrenal to make cortisol. Now, what you would expect is if this was all entrained simply by the body clock, is the following. You would expect very little to be going on during the nighttime. Then just before you wake up, you'd expect this big peak in cortisol, and then for it slowly to decrease throughout the rest of the day. But actually what you see is very low levels at night, certainly, but then it comes up and down. These great pulses happen early in the morning, and these pulses decrease as you go throughout the day. So it's a very pulsatile, oscillating signal which is circulating around the body. This occurs in every mammal that has been looked at. The rodents, of course, are nocturnal, so they have the biggest peaks of their corticosterone in anticipation of their active phase, which is during the dark, whereas in humans, we have the biggest pulses starting just before our active phase, which is during the light. So this has been found in all mammals that have been studied. So where does this come from? What's the cause of these oscillating signals of cortisol? Well, the obvious place would be maybe the signal from the hypothalamus, which is activating the whole system, is pulsatile. And I won't go through all the data on this, but there is actually no evidence for this at all. There is no evidence that your CRH signal causes these hourly pulses. So what we looked at was the interrelation between the anterior pituitary and the adrenal gland. So this was the work really of Jamie Walker and John Terry and myself. And basically what we found was the fact that ACTH, which is produced by the pituitary gland, hits the adrenal, and then there's a delay. And there's a delay of 15 to 20 minutes before the adrenal gland makes cortisol, which can then feed back and turn off the pituitary. Now, those of you that know the physiology of the adrenal, this shouldn't be a surprise, because cortisol is very lipophilic, which basically means it can pass through membranes very easily, so you can't store it. So every time ACTH hits the adrenal actually has to synthesize new cortisol, which is why there's a delay. But what you have here is a feed forward and a feedback system, and it's got at least one major delay in the ACTH hitting the adrenals and the adrenal gland. Those of you who are mathematically inclined will realize that any feed forward and feedback system that has a delay in it has to oscillate. And a good way to look at this, an example of this, is the older people among you will be aware of what showers used to be like. They used to be very slow in reaction. And so this just shows what happens with Mr. Burns and Smithers. So Mr. Burns gets into the shower, and it's a cranky old shower. He gets in and it says, oh, it's a little bit chilly. Come on, Smithers, I need it a bit warmer. So Smithers turns it up, but there's a delay before there's a reaction, and it's still cold. So he turns it up again, and it's still cold, and then it gets warmer, and Mr. Burns likes it, but then, of course, the signal makes it even hotter, and he goes, oh, it's too hot, Smithers. So Smithers then has to turn it down again, but it remains too hot because of this delay in the message, and so he turns it down again, and so we go round in circles. It gets back to normal, but then suddenly it gets round to being too cold again, and you get this oscillating signal of going to being too hot and too cold and too hot and too cold, and getting very difficult to get the right level of temperature. And it's same in biological systems that are feed forward and feed back, in which there's any delay. So what do we know? We know that there is a delay in this system, and John Terry and Jamie Walker looked at this, and they came up with a lovely mathematical model. Now, I don't want to go through this in too much detail, but just to remind you that the thing that turns on the whole of the axis is CRH in the hypothalamus. It has to produce CRH to activate the pituitary to make ACTH. ACTH then goes around the body to activate cortisol. There's a delay, and cortisol then feeds back on the pituitary to turn off ACTH. So the mathematical model they came up with is the drive from the hypothalamus here. This is the CRH drive in the y-axis, and the adrenal delay, the delay of ACTH acting on the adrenal to make cortisol, is in the x-axis here. And in the middle here, in this nice blue zone here, the Goldilocks zone in the middle here, is the area where the system mathematically has to oscillate. It simply, for mathematical reasons, needs to oscillate. Now, the important thing about a mathematical model is that you have to be able to test it. So again, our hypothesis is this. If you have high constant CRH levels, so the hypothalamus producing a constant but a lot of CRH, it'll fall outside this blue zone and you'll get a large increase of ACTH and cortisol and it'll stabilize at a constant level. If, however, you have an intermediate constant level of CRH here within the blue zone, then as soon as it's turned on, you'll get these lovely pulses of ACTH and cortisol. And we tested this, and we tested this in the rat. And the nice thing about the rat is that in the daytime, when it's asleep, it's producing next to no CRH. So we can give a constant infusion of CRH. So no pulses of this hypothalamic CRH, just a constant infusion of CRH. When we give a high concentration of CRH, get this large increase in corticosterone, and it remains raised. Then what happens when we give an intermediate level? When we give an intermediate level of CRH, you'll see this first big pulse, and then these beautiful pulses at hourly intervals come on afterwards. And then if we look at the first, I think it was 8 or 10 animals, you'll see that there's a constant infusion of CRH here, but despite that being constant, you've got these beautiful pulses of both ACTH and corticosterone about once every hour. So you have a subhypothalamic pulse oscillator. You have an oscillation which just emerges as a natural response to the interaction between the pituitary and the adrenal gland. So just to show you what's happening in pictorial form, let's say in humans at nighttime, early in the night, nothing's going on. And then as late evening and early morning, you start producing CRH. This gets the pituitary to make ACTH, which acts on the adrenal. After a delay, it makes cortisol. The cortisol feeds back, it turns off the ACTH. It turns off the ACTH, so the cortisol gets lower, then the ACTH turns on again, and you get this oscillating mechanism between the pituitary and the adrenal, causing oscillations of cortisol in man or corticosterone in the rodent throughout the time that this axis is active. So we now know then that from very early in life emerges a oscillating signal both of ACTH on the adrenal and an oscillating signal of cortisol. So one would presume that the system must have adapted to read these oscillating systems. So the first thing we wanted to do was to look to see how the adrenal gland has adapted to read an oscillating system, a signal of ACTH. So what Francesca Spiga and Eleanor Waite did was they looked in a whole large number of rats. You can't see the individual oscillations because this is the mean of a large number of rats. And that's what normally happens. This is their daily variation in corticosterone, which peaks before the dark phase. Then they gave them a synthetic steroid, methylprednisolone. What this does was it turns off ACTH. It doesn't affect the adrenal, it just turns off the ACTH. So you have normal adrenal glands, but they're not being stimulated, so they're not making any corticosterone. Now this is a lovely model because what we can do then is there's no ACTH here, we can give the ACTH back. And we can give back pulses of ACTH to these animals. And you can see that every pulse of ACTH we give results in a pulse of corticosterone. So it's this beautiful response of newly synthesized corticosterone with every pulse of ACTH. But then what Francesca and Eleanor did was they gave exactly the same amount of ACTH, but instead of giving it in pulses, they gave it as a constant infusion. And when they gave it as a constant infusion, absolutely nothing happened at all. The adrenal gland ignored it. So the adrenal gland was seeing the same amount of ACTH, but it was in a different pattern and it wasn't interested. So why might this be? Well, we've looked at this in a bit more detail. And the thing that you need to know is that the rate limiting step in the formation of cortisol, corticosterone in the adrenal gland is the enzyme STAR. And this is an enzyme which transfers cholesterol into the mitochondria within the adrenal gland, where it initiates the synthesis of cortisol. So STAR, the rate limiting step, is regulated by two major things: steroidogenic factor 1, SF1, which basically turns it on, and DAX1, which turns it off. So let's call this the accelerator that turns it on, and DAX1's the brake that turns it off. When ACTH comes round in the blood, it binds to the MC2 receptor in the adrenal gland. When it does that, it activates this receptor, and this receptor turns on the accelerator and turns off the brake. So it takes its foot off the brake, it inhibits the brake, turns on the accelerator, increases the activity of STAR, which increases the amount of cortisol that's made. Then cortisol comes back and it binds to SF1, and that this binding with SFM actually causes the creation of more DAX1, so it turns on the brake. So basically you turn it on, and once you have the cortisol, it increases the brake and turns it on, or turns it off. So you have a feed forward and a feedback system actually within the adrenal. And you can imagine if you have a constant signal, you'll be turning this on all the time, and then as well as putting the accelerator on, you'll be turning the brake on, and it won't be working so well. And what you've got is a beautifully tuned system that wants to see nice pulses of ACTH to maximize the effectiveness of producing producing the glucocorticoids. So we can see that the adrenal gland has adapted to seeing pulses of ACTH. What about pulses of CORT? Pulses of CORT go around the whole body. So you have pulses of cortisol in man, which are released from the adrenal. So they go into the bloodstream, into the venous blood, into the arterial blood, and they go around the whole body so that the whole body is seeing pulses of cortisol. What happens when the cortisol gets to the cells is the cortisol goes through the cell membrane and it binds to different glucocorticoid receptors, the so-called glucocorticoid receptor, which I've put in green, and the mineralocorticoid receptor in blue. When cortisol binds to them, they dimerize, which means they bind together, they translocate into the nucleus, and then they bind to glucocorticoid response elements, which allows transcription to take place. So basically, these elements go from the cytoplasm into the nucleus, and that's when they activate or sometimes inhibit the nuclear machinery. And we can actually look at this, and this was work we did with Diana Stavriva and Gordon Hager. Basically, this was looking in a cell line, looking at cells, and in this picture, all of the glucocorticoid receptors are linked to green fluorescent protein, so you'll see they're all green. So this is one cell here, and in the middle here is the nucleus, and you'll see that all of the glucocorticoid receptors are basically in the cytoplasm. So the design of the study is this, is we have no glucocorticoid in, so we have no corticosterone in, we give a pulse of corticosterone, we wash it off, a pulse of corticosterone, we wash it off, and a pulse of corticosterone. So when we give a pulse of corticosterone, the first thing you'll see is that the glucocorticoid receptors go from the cytoplasm into the nucleus, so they go into the nucleus. Now, this particular cell line is a very special cell line because it is artificially made to have about 2,000 glucocorticoid response elements all next to each other. So on the DNA, where the glucocorticoid receptor binds, there are lots and lots of binding sites all right next to each other. So you can actually see the glucocorticoid receptors bound to the DNA. So basically, when we give them a pulse of glucocorticoid, the receptors go into the nucleus and bind to the DNA. Then we wash it off. So we wash off the glucocorticoid, and you'll see that the glucocorticoid receptors come off the DNA, but they actually remain within the nucleus. Another pulse of glucocorticoids, they bind to the DNA, wash it, it comes off, and put it on again, and it binds. So you can see pulsatile binding of the glucocorticoid receptor to the DNA. What about the mineralocorticoid receptor? This has a slightly different dynamic. So we bound the mineralocorticoid receptor to M cherry so that it's red. And as you can see, it's in the cytoplasm here. When we put glucocorticoid on, it goes from the cytoplasm into the nucleus. But then different things happen. So this is what happens with the glucocorticoid receptor. So it goes from the cytoplasm into the nucleus, and at 20 minutes, it's all bound to the GREs, and then we wash it off and it's gone. With the mineralocorticoid receptor, it goes into the nucleus, we wash it off, and it remains bound. So basically, the kinetics of the binding of the receptors to the DNA is different for these two different receptors. So what Becky Conway-Campbell basically showed in her studies too was that at the peak of every pulse of corticosterone, you've got glucocorticoid receptors and mineralocorticoid receptors bound to the DNA. And at the nadir, at the bottom of each pulse, the glucocorticoid receptors come off and the mineralocorticoid receptors remain bound. And this doesn't only happen in a cell line. What I was showing you is in the cell line, and this now is showing you what Becky showed actually in the hippocampus, a very important part of the brain for memory. So you have a pulse of corticosterone in the blood, followed by a pulse of the glucocorticoid receptor binding to glucocorticoid response elements in the DNA in the hippocampus. You wash it off, the GR comes off. You put another pulse of glucocorticoid on, the GR again binds to the DNA, and then it washes off. And then if you look at transcription, so you look at the activity of the DNA in making glucocorticoid dependent genes, this is looking at a gene called period 1. You can see that every time you put on a pulse of corticosterone, there's a pulse of activity of the gene, which turns off, turns on, turns off, turns on, turns off, turns on. This is in the hippocampus in vivo in the brain. You can actually see gene pulsing with every single pulse of hormone. So then what Becky did was she came up with a nice model. So she looked at animals which make no corticosterone themselves, and she gave them back corticosterone either in beautiful pulses, physiological pulses like this, or she gave them back the same amount of corticosterone, but as at a constant infusion. And at the end of the last pulse, she looked at what was happening either in the liver or the hippocampus at the peak of the pulse and at the nadir of the pulse. And then in the animals that were given the constant infusion, she looked at exactly the same two time points. So this was Ben Flynn and Becky Conway-Campbell. So then, using chromatin immunoprecipitation, looking across the whole genome, Ben looked at the binding of the glucocorticoid receptor across the whole genome. So the difference in the binding. So basically, black means that there's no difference in binding, yellow means there's decreased binding, and blue means increased binding. So at the peak of that pulse, at the peak of this pulse here, you can see there's a lot more glucocorticoid receptor bound to the DNA across the whole genome. And then at the nadir of that pulse, there's absolutely no change at all. On the other hand, when we look at the constant infusions here at the two time points, you will see there's slight difference between the two time points, but the real thing that matters is that there's a great difference here between these and these. So the pattern that you give your glucocorticoid will change the way the glucocorticoid binds to the DNA. And of course, what's important is what happens to transcription. And as a measure of transcription, what Ben did, he also used the same technique to look at RNA polymerase II. And basically, again, RNA polymerase II is a measure of active transcription taking place, and anything blue is increased transcription, and anything yellow is decreased transcription. Remembering that glucocorticoids turn off a lot of genes as well as turn on a lot of genes. So again, looking at the peak and then the nadir, you'll see at the peak, a lot of genes are turned on and a lot of genes are turned off. And at the nadir, a few genes remain turned off, one or two may be turned on, but one or two turned off, but it's very different. If we look at the animals that were given the constant infusion, the pattern is really very different. So it actually matters in terms of the transcription of your genes, the pattern in which you're seeing your glucocorticoid. And if we look at messenger RNA expression profiling, and here we're looking in the hippocampus, let's say we're comparing the constant infusion here with the pulsatile infusion. This is just a heat map. You'll see that the mRNAs being produced with the constant and the pulsatile infusion are really markedly different. And this is just a few genes. I won't go through them in detail, but the amount of messenger RNA for lots of different genes is very different, although they've had the same amount of steroid, they've received it in a different pattern. So we know that the pattern matters, but what happens when you stimulate the system or you change the system? And obviously one thing that's been of particular interest to us is what happens in response to stress. And I showed you before that in a non-stress situation, your patterns throughout the day are regulated by the suprachiasmatic nucleus or the body clock. But if you have stress, this superimposes itself upon what happens from the suprachiasmatic nucleus. So you have superimposed stimulation of the HPA axis from some form of either external or internal stress. Stressing humans is actually remarkably difficult to do. So we've looked at two models of stress. One of them is obstructive sleep apnea, and I'll go over this quite quickly. This is work that David Henley did in my lab. Basically, he looked at the amount of cortisol secreted in patients with sleep apnea and then with treated sleep apnea using CPAP, which has recently become interesting in our patients with COVID. But basically, pre-CPAP, there was a very high amount of cortisol secretion for every pulse mass. So every pulse of cortisol is bigger before their treatment, and when they're treated, it goes down to normal. So basically what David showed was that patients have increased pulse mass when they have obstructive sleep apnea. And interestingly, OSA, as obstructive sleep apnea, is associated with metabolic syndrome, and it's also associated with cognitive dysfunction and affective disorder. And the reason I point this out will become clear later in the talk. So what other stresses can we look at? Well, one that is remarkably reproducible is what happens in coronary artery surgery. And I'm showing you here the mean of what happens to 20 patients who've undergone coronary artery surgery. This is work done by Ben Gibbison. And basically, the dark area here is the time of surgery. During surgery, to be honest, not very much is going on. It's really when patients get into the recovery room that they have this huge stimulus in cortisol secretion, which continues for 24 hours. Now, when you look at this, it looks as if there's a really very smooth response. But actually, this is a problem of a statistical problem of what happens when you mean what happens to lots of different people. What happens is you lose the signal. If you look at one particular individual, that's what actually is happening. So you get a pulse of ACTH in red here, and then you get these pulses, these huge pulses in cortisol, which are continuing for the 24 hours after surgery. And although ACTH comes down to much lower levels, every peak in cortisol is preceded by a peak of ACTH. And basically what's happening is that your adrenals have become very sensitive to ACTH secretion, producing these huge pulses of cortisol. So this is actually what's happening when you're giving a major long-term stress to the HPA axis. Now, does it matter? Is this relevant? Well, what Georgina Russell has done, she's wanted to find a way that she could create her own different patterns of cortisol in human beings. So basically, what I'm showing you here is physiology in red. So this is just one individual's pattern of cortisol over 24 hours. And then what Georgina did was she inhibited cortisol secretion, and she gave them a pulse, it gave them a pump, and the pump was modified in a way that it could reproduce normal physiological pulses. So she was able to reproduce normal physiological pulses. So the reason for doing this was that we can give these pulses, and we can, for instance, let the brain have either flat levels of cortisol, or we can give physiological levels of cortisol, and we can see what it does to the individual that we've done it to. So the study design in the study we published was we compared physiological cortisol, which is this, so late at night you start getting these big pulses of cortisol which decrease through the day. We compared it with exactly the same amount of cortisol, but given totally smoothly, then ramped up and then down again. Or we gave normal physiological, the way it's not physiological, sorry, the way we normally replace patients, which is to give them a tablet after they've woken, with one peak and then 2 peaks later. I'm not going to talk about this at the moment because I haven't got time to talk about it, but what I want to do is just to compare these two, because these are very similar, exactly the same amount of cortisol given in the same way. The only difference is the pattern in which they are given. So basically then what we did was we gave either this pattern, a smooth pattern of cortisol, or we gave a physiological pattern of cortisol with pulses throughout the day, giving exactly the same dose. And this was worked with Georgina and Konstantinos Kalafatakis. The first thing we did was we looked at sleep quality. And when we gave the constant infusion, sleep quality was very much worse than the sleep quality when we gave them normal physiological replacement. Then we looked at working memory performance, and we did what's called a 2-back and a 3-back test. The 2-back test is not very demanding, and we found that giving the smooth infusion, their working memory was good, and it was the same as the memory that they had when they were given the pulsatile infusion. When we did the 3-back test, however, which is much more demanding, the people with the constant infusion had a much poorer working memory performance, whereas the people given the physiological infusion maintained very good working memory performance. So the pattern of cortisol actually is important for the way your working memory performs. We were actually more interested in emotions, because the patients that we give cortisol replacement to, they often complain of lethargy, of just not having energy, not wanting to do things, and just being sort of laid back and just really not interesting. They have much higher rates of unemployment. We were much more interested in what the emotional state of these patients would be. So again, it was the same. We were doing the same pattern. We are either giving a smooth infusion of cortisol or physiological cortisol. And then basically the first thing we did was we looked at emotional bias. So basically we showed them either happy faces or fearful faces. And basically, normally you like to look at a happy face rather than looking at a fearful face. The patients giving the constant infusion looked at fearful faces and happy faces the same amount, no more one than the other. The patients given the physiological replacement were much keener or much more frequently looked at the happy face than the fearful face. So their attentional bias was towards the happy faces. We also looked at the recognition of emotional faces. So we showed them morphed faces, some that were very happy, some a little bit happy, some neither happy nor unhappy, some slightly unhappy. And basically we looked how well they recognized the emotion on the faces. And the patients with the non-physiological replacement, the smooth infusion, there wasn't much difference between their recognition of positive and negative faces. But interestingly, the patients given the physiological pattern of cortisol recognized negative faces less well. And interesting that this whole pattern here is the pattern that we see that develops when patients with depression are given antidepressants. So it's the patients given the pulsatile infusion show the response that the depressed patients have when they respond to antidepressants. I'm not saying these people are depressed, but there is a difference, and they tend to be motivated more towards happy faces than to unhappy faces. And finally, we did fMRI scans on these people, and I don't want to go into this in great detail, but there was major differences in the connectivity of the subjects who are on the non-pulsatile and on the pulsatile replacement. And the most important thing was that the connectivity between the amygdala and the insula was much greater in the patients who are having the pulsatile infusion. And this is an area which is activated when there's uncertainty in identifying emotional valence. And it certainly shows that this area is important in identifying emotional response. So the important message simply is that it is different when we give the same amount of cortisol in different patterns. So now I want to go on to something a little bit different, because I want to discuss now is how can we assess hypothalamic pituitary adrenal activity in subjects going about their normal lives. We can't take multiple blood samples from people all the time, particularly when they're asleep or when they're going to work. You have to bring them into hospital, and that's not really a very effective thing to do. So what we've done is that we have developed a new system that we have developed ourselves. And in fact, I think just today our website's come out. So if you want to know more about it, please look at www.urhythm.com. And you'll see much more detail about this, about our system. Basically, there is a pump which pumps saline through a little needle which goes just under the skin, and then it's collected by a rather clever little collecting device called Urhythm. So basically what's happening is a pump is pumping fluid through a little catheter. It goes under the skin. There's a semi-permeable membrane here, and everything that's in the body tissues then goes into the saline. It comes out again, and then we have a clever way in our Urhythm system to collect timed samples. So basically we can collect multiple samples over the 24 hours. This system can show you, for instance, response to ACTH, and I'm showing this is a work by Ragini Bake. She gave some ACTH at this point in time here, and this is levels of cortisol in blood. It goes up, the whole cortisol in blood, and this is the level of cortisol both in subcutaneous tissue, free cortisol in subcutaneous tissue, and free cortisol in the blood, which go up in parallel. And similarly, when we give them dexamethazones to suppress their cortisol, it goes down in blood and it goes down in tissues. This is in the mean of 8 people, and this is in just 2 individual subjects. So there's obviously a delay between what happens in blood and what happens in the tissue, but obviously this is something we would expect. Using this system, we can measure all sorts of different things. And this is something that Thomas Upton and Martin Van Hassen have been very interested in, is we can look at cortisol and cortisone and also melatonin. And you can see this lovely peak of melatonin overnight, and as melatonin comes down in the morning, you get this peak of cortisol and this peak of a cortisone. So this can happen, so we can measure that throughout the day, and we can also measure a whole load of metabolites as well, which I don't have time to talk about today. Just to show you that in the Horizon study, which we've been doing in collaboration with our colleagues in Bergen, Stockholm, and Athens, we have been looking at large numbers of subjects, and this is just the first 124 subjects looking at cortisol, cortisone, corticosterone, and aldosterone, and just this is individual subjects, and this is the mean, just to show you we've got this lovely circadian rhythm of that's cortisol, cortisone, corticosterone, and aldosterone as well, which continues to go up in a day when you stand up. We can measure vast numbers of different steroids, and these are just a few examples of what we can look at. And obviously we can use this also to define pathology, which is the next thing that we're going on to want to do. So what about children? One of the problems about children is, first of all, they don't really like you sticking needles in their veins, particularly if you want to stick lots of needles in lots of times to look at the pattern of what's going on. And also in infants, we have very little blood volume, and you just can't take a lot of blood from them. Well, we can use this system because we don't take any blood whatsoever. Because we are infusing saline through this catheter and collecting it at the other side, we take no blood from them at all. And this is a study, just one patient from a study by Daniel Fadulu. And again, this is cardiac surgery. This is in a child of 1 year, 2 months old, but we've done this down to ages of 5 days old. This child had a Glenn shunt put in. And again, you can see these huge pulses in cortisol in this child. And you can see the cortisone going up in a much smoother manner. And the important thing is here that, we don't have to take any blood at all. And yet over the whole 24 hours, we can have the pattern of how all of their hormone changes over the whole of this period of time. So finally, for something really quite different, and particularly with what's been happening with COVID at the moment, I've been very interested not only in what happens with your cortisol and your stress hormone levels, but I've been very interested how these relate to mood. I've been very interested to look at mood at a population level. And I've had the great joy and advantage of being able to work with Professor Nello Cristianini to actually be able to look at his fantastic data set on Twitter. So basically what Nello has is he has been able to look at 800 million tweets in the UK over the last 4 years. So he's been able to look at all of these tweets. Of course, they're anonymized. We don't know who they come from. But by looking at the words in these tweets, there's lots of information that you can gather. So just to give you an example, if you look for the word bus, and this obviously is pre-COVID, if you look for the word bus, you can see the word bus happens or is tweeted very frequently just before 7 until about 8:30 in the morning, and presumably that's when people are on the bus. Instead, this is the type, these are the months of the year, and this is the time of sunrise, and this is the time of sunset. As you go later on in the day, clearly people come home from work at very different times, because red is the most frequent. You know, people are coming home from work, but over a much broader period of time. So that's what happens when you look for bus. And for proof of concept, it's quite interesting to look when people tweet the word sunrise. And as I told you, this black line is when sunrise is, and you can see people tweet the word sunrise at the same time as sunrise is actually happening. So it's sort of proof of principle that we can use this type of tool, this type of mathematical tool, to look at what people are actually tweeting in a meaningful way. But of course, my interest wasn't, or our interest wasn't on when sunrise was, it's what people's mood was. And using psycholinguistics, we can actually look at the words that are being used, and we can give them a psycholinguistic valence to measure the value of that word and the frequency of the use of that word as a measure of the mood of that subject. And I can't go through this in detail for obvious reasons, but when we do this, we can look at these. Posimo is basically positive moods, words divining positive moods. And this is looking hours after midnight. And you can see that around early in the morning, you get this great increase in words with positive mood. It's bimodal, it increases to a peak about 8 or 9, and then it falls down greatly in the evening, and then it comes up again. And this is hours after sunrise. Similarly, you see this beautiful bimodal peak of words denoting positivity. The interesting thing is, if you look at this pattern and then you compare it with words denoting negativity, so negamo, negative emotion, you can see a completely different pattern here. So red obviously is when the highest frequency. There is very little negative emotion early in the morning. It increases and it peaks late at night, and then it comes down again. And this again, an hour after sunrise, you have the same particular picture. And the interesting thing is that negative emotion is not the mirror image of positive emotion. It's a totally different construct. They both have circadian rhythms, but their rhythms are different. And presumably the brain circuits underlying both of them are different. And this is quite important in understanding of psychology and when psychopathology in people with mood disorders. So to turn a slight bit of a circle, what we also did was to have a look over the year, and there is also a circannual cycle. So over the year, there is also a cycle of mood. And so if you look at negative mood here in brown, you can see that negative mood is maximal here in February and March, it's minimum in June, July, and it's maximum again in the winter the next year. So it goes up in the winter, down in the summer, and up in the winter. And interestingly, I'm not suggesting any causality here, but if you look at salivary cortisol levels also parallel this. So salivary cortisol levels are maximum in the summer and their minimum in the winter, and their minimum in the summer, and they parallel the two. So there is a timing association, but all I want to show you here is that there are timing of many, many different systems, and all of the systems in our body are undergoing all sorts of oscillations. There may be yearly oscillations like this, there are daily oscillations, and of course you have the oscillations which occur much more frequently, the ultradian oscillations as well. So in conclusion of my talk, let's concentrate on the glucocorticoids. The glucocorticoids are secreted with both the circadian and ultradian oscillations. Stress results in increased amplitude of glucocorticoid oscillations. Each ultradian oscillation is associated with episodic glucocorticoid receptor activation, whilst mineralocorticoid receptor remains occupied between pulses. The ultradian pattern of glucocorticoid secretion determines tissue specificity and genomic response. Pulsatile cortisol secretion affects clock genes. I haven't really talked about this. It affects sleep and your activity cycles, emotion, your memory function, emotional response, and brain connectivity. And with our new techniques of automated ambulatory hormone analysis, we should be able to reveal changes in hormone dynamics associated with endocrine, inflammatory, metabolic, and psychiatric disease. Publicly available data sets can now also be used, and these can be used to investigate surrogates of mental health at a population level. And I think in the present COVID time, this could be very interesting and very important. I just want to say that obviously this work was done by lots of other people, and I have the pleasure of talking to you about it. The molecular and physiological studies have been led by Becky Conway-Campbell and Francesca Spiga. The engineering for making our automated sampling system was originated by Jack Leandertz, but is currently being carried out brilliantly by Robin Crossley and Jeremy Gardner. The clinical neuroendocrinology by Georgina Russell, Thomas Upton, Regini Bate, Konstantinos Kalafatakis, Ben Gibson, Daniel Fadula, and Gianni Angelini. Mathematical modeling, and this is the key to this particular talk, all of this really came out of a time when John Terry came and sat in my lab, talked with me and all the people in my lab, and we actually realized the importance of mathematical underpinning for all of the work we were doing. So John Terry and Jamie Walker, who was our joint PhD student at the time, who really set all of this up. And since that time, further work has been done by Eda Zavala, Diane Fraser, and Mohammed. And we've had lots of collaborations with Ida Kemmer and Martin van Fassen in Groningen, NIH, Gordon Heger, Dana Stavriva, and the Horizon 2020 I showed you about, which did all of these patients, also patients with Cushing's disease and Addison's disease, was with Øystein Huseby and Paul Methley in Bergen, Ulla Kamper in Stockholm, and Stelios Tsagarakis in Athens. I'd like to thank all the people who gave us money to do all of this work and have all the fun we've had doing it. And finally, a photograph of what I should have been doing this summer before all Glastonbury was cancelled. Thank you very much indeed.
Thank you so much, Stafford. That was fantastic. Let me just start my video. So thank you very much. That's probably, unfortunately, the quietest applause, but I'm sure I'm clapping on behalf of all the attendees. Listen, we've got a number of questions, if you're happy to answer some questions from our audience. Sure. But I might abuse my chair's privilege and kick off. So I was just really interested in the work you presented at the end with the relationship between positive and negative emotions and the timings of those. I just wondered, obviously, in terms of the rhythms you presented us during the talk, you could see some immediate correlations between those and these positive and negative emotions. But I just wondered, had you considered the impact of other external factors? So I'm thinking in particular alcohol, which you might think would peak in terms of alcohol consumption in the late evening, which might then lead to negative emotions being more prevalent in the late evening and early morning. Has that been looked at all or excluded as a factor in your studies?
At this stage, what we're basing it on is looking at 800 million tweets there's going to be a lot of noise in the system, but because we have such large numbers, I think the noise per se is probably not going to be a problem. But having said that, of course, there are things like that that we would want to do, but because this is all anonymized, and it has to be for ethical reasons, we can't know who amongst the people we've listened to has been drinking alcohol or when they're drinking alcohol. But I have to say that your question is a very valuable one, and actually the COVID experience may actually give us a way into this, because people's lifestyles have changed a huge amount. And so they won't be doing the fixed going to work and coming back at the same time that they were before. I suspect their drinking habits and timings and things will change. So there are ways that the changes that are going on at the moment might be able to give us hints about this, but we can't manipulate the system. Unfortunately, it would be nice to be able to intervene and change something like drinking. It would be lovely to be able to do that, but unfortunately, in our society, that's not something we can actually do.
Sure. Well, listen, I'm going to go to some of the questions from the audience now, and I'm going to kick off with one from an anonymous attendee who says, "Fantastic talk. The question is, what do you feel are the most exciting future directions of this research in the next decade?"
Well, I think where some of this is, there are two areas. First of all, in terms of hormone replacement, or in fact, a lot of medications. We have in the past been just giving medications at a time what's been convenient to us, like you take something first thing in the morning because that's when you remember it, that's the easiest time to take it. And when we give hormone replacement, we give it maybe in the morning, in the afternoon, in the evening. It's becoming apparent that that isn't very good physiologically, and we should be able to create new ways of treating people with more physiological replacement therapy, which may help people feel a lot better. In terms of other areas, in terms of personalized medicine, using our automated sampling device, we will be able to look at the whole metabolome, all the hormones, vast array of things that are going on in any individual, which may be putting them at risk of various different diseases. We should be in a position that we should be able to prevent a lot of diseases by using this in a targeted way to look when people may or may not be at risk of developing diseases. So I think a better view of the way we treat people, and it could be not just hormone replacement, treating cancers, for instance. It seems that the time of day that you give treatment may well be relevant. All of these things, understanding better the timing of treatment and understanding better the timing of your metabolic response to things should improve, I would hope, human health.
Yeah, I think you're absolutely right. I think this timing of the relationship between drugs and also the internal physiological function of the human body is going to be really critical. Another question we had is regarding your comments around the emotional state of patients treated with cortisol replacement. Is there any relationship to people with apathy as well in this sense?
Oh, well, I would define the major problem of a lot of people on on cortisol replacement, their major problem being apathy. They are apathetic, which is why, not all of them, but a lot of them are apathetic, which is reason they just don't have the energy to do things, why they're not employed. They just don't have the energy to do things. So apathy is a major symptom of that disorder. Now, whether we can project this to other causes of apathy, we just don't know. So, it is conceivable that some other forms of apathy may well be related to disorders of patterns of cortisol, but we haven't done this. We haven't done this work at all. But apathy is a really important area. It is an under-investigated area, and it is certainly an area that we are looking into ourselves, and we are very interested in. So it's a very important question, but until we have a bit more data, I wouldn't want to say that this is going to be the answer, but it's probably part of the answer.
Great. We've got a question from Gareth Leng. We might know him.
We might.
Gareth is asking, are you able to resolve pulses of cortisol with the continuous microdialysis system that you've developed?
The answer is yes. It depends how frequently we take it. The way we have been doing most of our sampling at the moment is collecting samples every 20 minutes. And of course, when we do that, we're averaging the tissue levels over the period of that 20 minutes. So we would then only be picking up the bigger pulses, not the smaller pulses. But if we increase the frequency of taking samples to every 5 minutes or every 10 minutes, which is feasible. It depends really on the sensitivity of your assays and how good your recovery is of getting whatever it is in the tissues into your microdialysis system, then the answer should be yes. So theoretically, yes.
Fantastic. We've got a question from Eloise Hearn. How can you see the treatment of Addison's disease changing in light of some of your research?
I think there were two things that are really obvious from our data. So I didn't show the data because it's not published yet, and obviously I'd need to discuss it with my colleagues. But what was really obvious from our data is that the levels of hormones in patients given normal replacement therapy is extremely unphysiological. First of all, they only take their first dose after they wake up, and they often feel absolutely awful. It seems that the levels of hormones before they wake up are incredibly low, so they're basically cortisol deficient before they wake up. So we have to find a way of either giving them a delayed release cortisol that goes up before they wake up, or even better, finding a way of giving them pump treatment or some other treatment which will give them pulses of cortisol in the morning before they wake up and pulses during the day. We have ideas about how we can do this, and we have ideas of how we can do this not only by pump, but by giving them particular types of oral treatment as well. I'm sure we will be able to give treatments that increase the level so you've got cortisol in your blood when you wake up, and also to give it pulsatile over the day.
Okay, that's fantastic. So another question now from Sandra Mazine. So I think she may be asking in the context of some of the Twitter data, could you actually perhaps get a set of participants who might be willing to kind of share additional data with you regarding sort of other aspects of their life, so that you could actually start looking at more specific relationships between these different factors that you've discussed?
The answer to that, that's something we'd be extremely keen to do. It's a numbers game, and so you need quite big numbers, but it depends on what the question is you're looking at and whether there is some way you can influence it. So if you actually do something which influences what's going on, then the numbers of people you need is rather less. So the answer is yes, and it's something we're very, very keen to do. The ethics of some of this is something we have to be very careful about. But if you have volunteers, then this is something we can do. There are ways using social media of actually getting volunteers to do this type of study, and it is something that we are looking into. So, yes.
Fantastic. Changing topics slightly, so we've got a question from Simon Privet, who's talking about epilepsy. And Simon says that in his experience, lots of people with epilepsy find that seizures may follow a pattern over the course of a day, resulting in seizures happening at specific times. Do you think it's possible that your work could highlight some kind of balance in hormones in the brain, which could impact on seizures in certain people?
Yes, I mean, I think there are two things, and I'd like to answer in two parts. One thing that our system can do is it can measure your tissue levels of anti-epileptics throughout the 24 hours. And it may be that some of these drop at particular times of day, which might make you more susceptible. And that's something we would be able to measure over the 24 hours. In terms of hormones like cortisol, we just don't know. I mean, there's always been this concept that a lot of people with epilepsy complain of, that the relationship between stress and epilepsy. And it is quite possible that either high or low levels or changing levels of cortisol may change your susceptibility to getting an epileptic episode. There are things that I would like to do. I would love to do a study in which we have patients with epilepsy in which we block their adrenal steroids and we can give them back cortisol in different patterns. And so we could see whether or not different patterns of cortisol replacement change the incidence of seizures at different times of day. So the answer is that we don't know, but it's a line of inquiry we'd like to follow.
I mean, just adding my own personal perspective as someone experienced in epilepsy research, I mean, I think epilepsy actually could serve as a prototypic neurological condition in this regard, because the dynamics of the symptom of epilepsy, the seizure, is such that you can really study the interplay between these hormonal factors and the seizure phenotype in a meaningful way that may be more challenging for other neurological conditions where the timescales of the symptoms may be much longer. So, for example, in depressive episodes, the timescale may be months or even years, which makes it quite challenging. So I think epilepsy is a really interesting area to explore. We're getting lots more questions, Stafford, if you're happy to continue.
Yeah, I'll just have a drink of water.
We've got one here from Duncan McGregor. So he talks about the administered continuous signals compared with the pulsatile signals. So although matching the total dose are at a low concentration, what happens to the response if you gave a continuous signal that matches the peak concentration of the pulsatile signal?
I'd love to know the answer to that. I mean, but the simple answer to that is that these are incredibly complex, time-consuming studies. And I would love to be able to answer that question, but it would be a massive amount of work and it would need somebody to give me a grant to be able to do it. I would like to be able to answer it. I can see where he's coming from. Basically, does it matter what peak you reach with each pulse? Is that what matters? And if you gave a constant infusion, would it do the same? And I mean, I suspect the answer is it would be very different. It wouldn't be the same. Certainly from the molecular studies we've done, we would expect it to be very different. But I can't answer the question because I haven't done the study.
Great. Well, thanks for that. So another question now from Barath. Barath is asking us, what are the downstream effects of pulsatile GR activation on the transcriptome or proteome? So he says, in other words, can effects of pulsatile cortisol be detected in the expression of the transcripts you're interested in?
In the transcripts, definitely yes. And so we've certainly done RNA-seq, and I showed you one RNA-seq from the hippocampus showing you genome-wide differences, and in the liver there are huge differences as well. So transcriptomically, yes, there are very major differences. As far as the proteome is concerned, these are studies that we would like to do. So I would expect there to be, but again, we need a bit more funding to do that, but I would like to be able to answer that question.
Fantastic. Question here from Kate Godfrey. So Kate's wondering, was there any research that you're aware of that looks at these hormones and their patterns in relation to delirium, where we see a high prevalence of in elderly and or critically ill patients?
Nobody's done it. So sadly, there are very few people who have done these studies. They're very work intensive, and you need these automated sampling systems to measure multiple hormones, and not very few people have the ability to do that. So the amount of information out there is extremely limited. Delirium is really interesting because it's one of the few areas where CRH antagonist is actually quite effective. So in a way, I would expect there to be differences in delirium, but nobody's done it.
Okay, so we've got another question, this time about hypoglycemia. And in individuals with impaired awareness of hypoglycemia, they often show a blunted cortisol response. Have you, or do you know if anyone has looked at ultradian patterns in these individuals? And if the pulsatility was lost, could it be put back somehow?
Nobody's looked.
No. Okay. And let's see, there's another, here we are. So we've got another question from an anonymous attendee here. In your Twitter studies, were the words you looked at just English language? And have you, or would it be possible to take into account words from other languages to better understand if there were regional or any racial variations?
The answer to that is that all of ours were English. The psycholinguistics that we use is, has been extremely well developed for the English language. But it is possible, and certainly I know that Nello is looking at Italian and is looking at some in Italy as well. So it is possible, but you need to be able to valence all of the words. It is actually really quite complicated how you do this. I mean, for instance, you have to be very careful if you use the word good. You must be careful what the next word is, because if it's good evening or good morning, that isn't an expression of anything, because that's just a greeting. And so the science of using these words is actually really quite complicated. And so you can't just use another language unless somebody has actually evaluated the ways of using words in that language in quite a detailed manner.
Okay, so we've got a couple of questions left. So the next one from Linda Brown. We know that going to sleep, we know going without sleep for a long time can be dangerous. Is there equivalently a dangerous level, low level, for example, of cortisol? What are your thoughts on that?
A dangerous level of cortisol?
Yeah.
Yes, I mean, the people who've got Addison's disease before they're diagnosed have low levels of cortisol. They can cope pretty well until it falls beneath a certain level. And then when that happens, anything else that happens to you, if you get flu, if you get unwell for any other reason, that's when you crash. So you can cope, but you probably don't feel well. You probably feel non-specifically unwell, lack of energy, lack of wanting to do anything. But it's probably when something's superimposed upon that you actually crash and get really ill.
Okay, and a final question, how do these rhythms of cortisol relate to other hormones, for example, insulin or estrogen or thyroid hormones, etc.?
That's an incredibly interesting question. Almost every hormone that is an active hormone is pulsatile. So insulin is extremely pulsatile. And basically, you have feedback from blood sugar. There's a feed-forward feedback system between blood sugar and insulin secretion in the islet cells of the pancreas. And there are great pulses of insulin, and those pulses are seen mainly in the liver, and they're much smaller when they go around the rest of the body. But the only hormones which really don't pulse are ones that are pro-hormones, which are non-active. Things like thyroid hormone, which is not really an active hormone itself, it's a pro-hormone for making T3, and the half-life of thyroxine is about a week. That doesn't oscillate. But almost all other hormones, whether it's parathyroid hormone for calcium, your reproductive hormones, so, testosterone, estradiol, they all oscillate.
When you say they don't oscillate, is it literally they don't, or that the actual time scale of the oscillation is just very, very slow? So you mentioned it had a half-life of a week, potentially.
I'm not aware of anybody who has done very long studies on this, so I don't know. It is quite possible they do have a slight oscillation over a very long time course, but nobody would have measured it. Well, not to my knowledge anyway. Okay,
well, listen, Stafford, thank you very much for that question and answer session and for the fantastic talk that preceded it. Sandra Mazine's come back in actually with another question, which is quite timely, asking when do we get another conference like this one? Actually, we were just going to let you all know what was going to happen. So we hope that you've all enjoyed this conversation. We would welcome your feedback. So we've seen some comments on the webinar chat, but do also drop us a line via email or Twitter or Facebook. We're really keen to get your feedback. We do have another conversation booked in, and that's going to be on Wednesday, May the 20th, the same time at 3 p.m. And our speaker then is going to be Professor Blanca Rodriguez from the University of Oxford. She is a professor of computational medicine and a Wellcome Trust Senior Fellow. Her work involves primarily looking at the heart and heart rhythms and disease. So I think that's going to be another really fascinating conversation. We'll be advertising all of the details of that on our social media channels. It'll be taking place via Zoom webinar again, so we hope to see many of you there then. One final thing, we're looking to establish a group of interested members of the public to actually become involved with helping us shape the research direction of our centre. And if you're interested in this, it would be great if you could get in touch. I've just brought in Caroline, who's our Communities Engagement Manager, just to sort of say a few words about the sorts of things we might be looking for and how you might be able to get involved. Caroline.
Absolutely. Firstly, thank you to Stafford for an absolutely fascinating and thought-provoking talk. So I need to say thanks there. But yes, absolutely. So as John was saying, one of the things that the Centre for Systems Modelling and Quantitative Biomedicine is really interested in doing is making sure that we're doing a lot of public engagement, public involvement with our research. So this is part of that, these SMQB Conversations. But beyond that, we're also looking to establish a group of friends, or our amigos group as we call them. And this will be a group of public volunteers that are interested in helping us ensure that science is relevant to public groups, and that the work that we're doing reaches a wide group of people. So that the AMIGO group stands for Advisory Members Involvement Guidance and Outreach Group. And the idea really is that you work with us to help with various things. So it might be, for instance, helping our researchers think about how we might do public engagement linked to their research projects. It might be looking at papers that they've published and helping them with lay summaries or that sort of work, but also helping us think about how to do public engagement as a centre, and assisting our researchers with various projects, thinking about social media, etc. So if any of that sounds like something that you might be interested in, then please do drop me an email. I can give you much more detail about what type of thing we might be interested in, but we're not looking for any specific expertise, just an enthusiasm to be involved. And we're very, very keen to include people who've got lived experience of health conditions or particular diseases, but also other people who might have personal, professional backgrounds and skills in various things. So as I say, no specific expertise we're looking for, just an enthusiasm to help us engage people with contemporary science.
Thank you so much for that, Caroline. And as we said, we'll be advertising this through our social media channels, and also we'll hopefully have a bit more information as part of the registration for the next conversation, which, as I mentioned, will be on Wednesday, May the 20th at 3 p.m. So for now, it just leaves me to thank Stafford one more time for an absolutely fantastic talk. Thank you, Stafford. That was incredible. And thanks to all of you for taking the time to come and engage with us. We hope you've enjoyed it, and we'll see you again soon. Goodbye, everybody.
Bye.